Okay, to get you started on this week's lab, I thought I would show you some tools here and how to do this. So when you open up this web address, you'll see here, that's it. If you have trouble finding it, if you can't, if you should be able to click the hyperlink and it should take you right to it, the hyperlink that's in the document. So we need to build a circuit that's in the one I asked you to build. So here's how you do it. So grab a resistor. Let's see if this is the right one. It might not be. Nope, that's not the right resistor. See how that only goes from 1 ohm to about 100? So we want to get rid of that puppy. So what we'll do is we'll just do this. Nope, I got to drag it back over. There we go. I'm not too familiar with this myself. Here we go. This resistor choice gives you larger values. And really, we want to use larger values because small valued resistors are kind of ridiculous because when you put a significant voltage across them, they're going to draw a lot of current and they'll burn up. And believe you me, if you have like a 10 ohm resistor and you're trying, if you put 10 volts across it, that has to have significant power and it's a huge resistor. It's just not something you see all the time. So this is more realistic. So I'm going to click on this resistor and we're going to make this is R1, 1100 ohms. See that? Now we can also do this. You can click on values and that way you can keep up with what you're doing. Okay, so let's drag another one over here. I'll go on and lay them out like we need to. Something like this. Now we're going to click on this one. This will be R2. I believe it's 1500, right? So we'll choose 1500. Okay, and then finally the last resistor here. And this shall be about 1900, right? Okay, so those are some reasonable values for resistance. And let me say this. Just as a rule of thumb, think about it. You have Ohm's law. V is equal to IR. So if you have voltages, your supply voltage is on the order of a volt. It can be anywhere from, it can be anything, but, generally we use small voltages, a volt, 10 volts, 5 volts. Just say 1 volt. If you have kilo ohms, 1,000 ohms, kilo ohms resistance, you're going to have milliamps of current. You get that? They're inversely proportional. V is IR. Kilo ohms, milliamps. So for 1 volt supply, if you have kilo ohms, you're going to have milliamps. If you have mega ohm, you would have microamps. So those are very common values in the most common circuits. Okay, so let's play with this circuit here. So let's move this up here like this. Let's spread it out. We can see what we're doing here. So that's going to be our circuit, right? So let's get some wire. Okay, now make sure your wire resistivity is as low as it'll go. We want to ignore that. We don't want to complicate matters. Okay, so we're going to have a connection there, right? I'll go on and connect it up and then remove the wires that we need to remove to put the ammeter. Ammeters measure current, voltmeters measure volts. Okay, now we have another wire here. I'll put one here like this. And then we can take another wire and do this. I can split that current up right there, right? The current will be split right there. I can put another one here like this. Now we're getting somewhere. Now let's move these over a little bit. You might can make a pretty one the way you want to. It doesn't matter how you do it as long as you get the top. It's called topology, the circuit topology correct. So we'll put in a wire there. Do another one here. And then now we can just look. I'm going to put the meters here, the ammeter. We'll talk about that. And then I can just connect these ends like that. That's fine. It's all looking good, looking nice and neat. So another thing we want to do is we want to measure conventional current. You can go back and forth. It really doesn't matter, but conventional current's the way you learned it in the textbook. This choice here, that'll be the direction that positive current would flow. But really, in a real circuit like this one, electrons are what carry current because, the conductors have free electrons in them, right? And by the way, resistors are just conductors that are doped with a certain amount of insulators to make them more resistive, right? Okay, so now we're going to take let's get our battery, and I believe we want, no, that's the battery choice I believe we want. Let's see if it is. So, oh no, that's a monster. We don't want that. No. We want to go up here and get there we go, a more realistic, smaller battery, a smaller power supply. This is our power supply. It's not really a battery because this would be like a benchtop power supply in the lab where we can adjust the voltage, tune the voltage, so to speak. Okay, now what I'm going to do, so I'm going to bring another wire in here like this. See, I could just connect it there, right? But I'm just trying to make it look kind of good, kind of like a textbook. I'm not going all out, but this looks sort of like it would in a textbook. There we go. Now we have it connected. So you can do something like that. You don't have to do this as long as it works. Now, the next thing we need to do is we got to realize that we're going to be changing this voltage here. I think let's see, is it 20? Let's see. We're going to be using 20 volts right here, 20 volts, 45 volts, and 70 volts. Okay, so let's say we start with 20 right there. That'll be our first voltage, the lowest voltage. Now, what happens here? Let's just look at it run. So if we put it on conventional current, and why is it not running? It should be running. I don't know. Everything should be running. But it's not. Oh, it is running. Okay, never mind. I can see the arrows moving. If I crank this voltage up, wow, I was freaked out for a minute. Yeah, see them moving a little bit faster. So that's a very small current, obviously. So let's go back to 20. So that's okay. I just wanted to have the values just a little bit more realistic than the ones they provide. Okay, there we go. The current, it is, those arrows are moving. Okay, there we go. Okay, now we need to measure the current in 3 places. Why? We want to measure the total current. Now, the total current, notice that this resistor experiences the total current in the circuit. So I can put an ammeter here that measures the current along this path here, right? I could put it here. It doesn't matter where I put it, but I'm going to put it here. Notice I can put it here, here, or here. So I'm going to click this loose and get rid of that for now. Okay? And what I'm going to do is I'm going to bring an ammeter over here. That measures current. It's kind of interesting. Why don't they call them amp meters, right? Anyway, there we go. Make that look a little better. It's not. There we go. I'm trying to make this look a little better. It's not cooperating with me. Anyway. Oh, well, that's good enough. All right, now, that measures the total current. So the total current in the circuit is 0.010 amps. That would be 10 milliamps. See that? Because like if you had a 1 here, it'd be 1 milliamp, 10 milliamps, 100 milliamps, 1 amp. Okay, now we need to get rid of this, right? We need to cut this one loose and put an ammeter in here. I might just leave that segment short like that. There we go. That's not so bad. There we go. Now, see how this current's less than that one? Now, what do you think the current here should be? It's pretty obvious that it should be what? If we put an ammeter here, okay, I need to practice. But anyway, you get that. That works, but I just don't like the way it looks. But anyway, that's fine. Now, you're going to have, notice how the sum of these two currents is this current. Now, it's a little bit off, right? Because that current plus that current would be 0.011. And the reason for that is the precision afforded by the ammeters. But that's okay. That's part of this lab is the ammeter's precision is what gives you a little error. That's fine. That's sort of realistic in a way. Okay, so there we go. We have milliamps resolution. See that? We're to that's our significant digit. That would be, if that was a 1, that would be 1 milliamp. That's our resolution. Okay, there you go. Now, so this is going to be an easy thing for you to do. Now, we get the voltmeter, and we can measure the voltage drop across each resistor this way, right? Now, notice something that you should see is this, that first of all, let's go back. This 1100 ohm resistor experiences all the current. The current gets split right here. Some of it goes this way and some of it goes this way. Now, more current's going to go this way because this has less resistance than this. So the larger current, and you see that. You have more current up here because you have less resistance. And then the current joins back up at this point, and it's back to 0.01. If you put an ammeter in here, you would see that you would get 0.10 amps. You could do that if you want. Now, let's measure some voltages. What could we predict? Okay, first of all, we know the voltage. Okay, let's measure our battery and make sure our meter's working. So if we do this, we get 20 volts, see? Now, let's do that. Now, first of all, let's look at the voltage drop across the wire. It's a conductor. It should be 0, and it is, see? So we don't have any resistance here, so the voltage drop. Notice that if I make the wire resistivity high, you get a voltage drop. See that? So let's leave that resistivity tiny. Okay, now, let's measure the voltage drop across this resistor here. Whoops, that's going to be negative. I need to you put the high potential side on the side where the current comes in. Okay, there you go. Now notice that it makes sense. We can't have anything more than 20 up here, right? I mean, that would be violating conservation of energy. So you could predict what the voltage drop across this parallel circuit up here is. It would be 20 minus this 11.35. See that? So this voltage drop across this resistor is 11.35. So if we measure the voltage drop across this, now let's do that. 20 minus 11.35. What is that? That's 8.65, right? So we should get 8.65 if I do this. See? As predicted, 8.65. Now, notice that it doesn't matter where we put it. We can put it here. That's still 8.65, still 8.65, still 8.65. Think about that. We can move this one here and here because all these points are connected together. It doesn't matter. Now, let's get the voltage drop across this resistor. Notice notice that it's going to be 8.65 no matter what. Both of those resistors that are in parallel see 8.65. See that? 8.65 volts, 8.65 volts. So I'm thinking that that should really get you going. And what I want you to do is make a real pretty circuit. See if you can make it look a lot better than that. That's kind of goofy looking, but it looks okay. Make a real pretty circuit and take a snippet of it and include it in your lab report. And ask me questions, if you have trouble. I think you'll find this to be, it's pretty fun. I think you'll find it to be okay. Where you'll have trouble is probably graphing, and I'll have to probably help you out a little bit. Maybe not. We'll see. See if you can figure out how to graph it. But anyway, there you go. Now, oh, by the way, if we let's crank up this voltage beyond. We're not going to use a voltage like this. Now you can see the current move. And notice that if we go to electrons, the current goes the other way, right? See, electrons go the other way. See them moving? They're moving counterclockwise. But if we go with conventional current, it's clockwise. There you go. So I hope this helps you out a little bit. So remember, you're going for 20 volts. You got to measure all the currents and all the voltage drops at 20, 45, and 75, I think. No, 70 was the last value. There you go. Those three voltages. And it would be nice to get more because, I hate to do graphs with 3 points. But, hey, it proves the point. It's good enough. Okay, hope you enjoy this lab.